So this session is called Making Hybrid Manufacturing Dead Easy Part 2. So we will have an introduction about Directed Energy Deposition or DED, and then we will go through some examples of how APlus can help you to program your toolpaths using hybrid manufacturing. The first example will be a 3D surface coating, followed by building a roll die, building a supportless overhanging geometry, which is one of the big challenges in hybrid and additive manufacturing. One layer multiple material, which will describe one of the great utilities of APlus called AMZ layer merge. Hybrid wire arc additive manufacturing example. And the final example is the thermal modeling of the DED process. So what is DED additive manufacturing? Additive manufacturing is used to manufacture parts through layer-by-layer deposition using 3D CAD models. It has different categories. They are binder jetting, material extrusion, material jetting, powder bed fusion, sheet lamination, back polymerization, and a directed energy deposition or DED. It is used for different functionalities. The main three of them are near net shape parts, is building a part from scratch using hybrid manufacturing. Repair a broken part, you know how expensive it can be to build a new part or make a new part, but with DED you can just repair it using hybrid manufacturing possibilities. And feature addition, if you want to add a boss or a feature to your parts. So directed energy deposition uses a direct energy source to melt and fuse deposited materials. There might be different types of heat source: laser beam, electron beam, wire arc, and plasma arc. The video you're watching is a video by Primo Additive, one of our industrial partners in Italy, making the blade on a radial substrate using a laser dyne 430 machine. On the second picture, you can see different type of laser powder and wire arc machine. So on the left, you can see a laser powder machine. There is a focused laser beam on the middle and the powder nozzles on the side in order to deposit the material. It can be the other way around based on how our manufacturers make their machines. Also on the right, you have electron beam and on the middle and the metal wire on the side in order to deposit material using wire arc. So let's move to our examples, how APlus can help you to program. So on the left, you can see a part which is being coated on the picture on the right. This is an excellent example to show for coating purposes because this has different type of surfaces: flat surface, fillet surfaces, holes, and bosses. In order to have a 3D surface coating, we have a very cool toolpath, which is called AM multi-axis surface, as you can see. So we have 6 different AM multi-axis toolpaths for 6 different surfaces of this part. Surface 1, 2, 3, 4, 5, and 6. So you can have 2 different strategies while using multi-axis surface. One of them is a raster pattern. So you will have a raster pattern coated on your surface. It's a very good option for flat surfaces, as you can see on surface number 1. The other strategy is using a chain and offsetting it on the surface. So for this fillet, we actually use the boundary chain, and it makes your tool paths by offsetting the chain all over your surface. So this is very good for fillet surfaces as well. After that, we are going to see the 2 other holes on the boss. Again, you can choose any chain that you like to. It will try to give you the best tool path based on that, but if you choose the right chain, you will definitely have a better tool path, as is shown on this example. And finally, we will see the final hole, which is coded. This is how you can use AM multi-axis in order to code. So let's move on to our second example, which is building a roll die using hybrid manufacturing. So, you know, if you want to make this roll die here with traditional manufacturing processes, you will have to have a very big stock cylinder and do a lot of machining in order to have this rolled up. But by using DED and some surface finish at the end, you can have it way cheaper and way faster. So in order to do that, we have a tool pass called AM radial slice. So what it does, it actually slices your model like the normal slicer, but on a radial basis instead of a planar Cartesian system. So let's see this example. So this is the AM radial slice toolpath which you use there. I'm going to show you the back plot. I'm going to show you the right view to see how it is basically sliced radially instead of planar. So this is the first slide, second slide, and third slide. If I show you the isometric view, you can see that it is basically building your parts on a radial basis. And I made sure to add some extra layers on the top in order to have a final machining, which would help to have a smoother surface at the end. So in order to do the final machining, this is the APlus AM part model, the simulated additive manufactured part model, which is compatible with Mastercam. It can be used as a stock model for the final machining, which is used on this example. So as you can see, instead of doing a lot of machining, wasting a lot of material, but just one directed energy deposited toolpath and one just very simple and fast surface finish, you will get your roll direct. Let's move on to our third example, which is building a supportless overhanging geometry. So this is actually a real example that our research team worked on. As you know, building the overhanging geometries without any support material is one of the biggest challenges of DED. So we use this dome. If one wants to build this dome and slice it on traditional, just a normal slicer, if you choose the A geometry, you will have this much overhanging angle. If you rotate it and use the B one, you will have these overhangs. And if you use the C situation, again, you will have overhang angles. So what is the solution? Does that mean that we cannot make this dome without any support material? No, of course we can. By using APlus on the right way and making your toolpath, you can actually do it. So we did that, and not only with one solution, but also with two of them. So the solution one is a wedge-shaped partitions with 5-axis toolpath. So we basically split that dome into 4 different sections with 45 degrees angle, and chose 4 different toolpaths and built them on top of each other. For each of them, we always had the nozzle tangent to the part. Therefore, we made like this wedge first, and then the second one, and the third one on top of that, and the fourth one. And we actually were able to build the part. As you can see on the right picture, we made the dome without any support material by using 4 different wedges. But it usually might be easier to have your nozzle normal to your surface rather than having it tangent all the time. So is there a solution to build it like that? Of course, there's another wedge-shaped partitions, but in order to do that, we will have to split the angle to the half, which means we will have 8 different sections and 8 different toolpaths, and we will build them on top of each other by having the laser always normal to the part. So this is how we build it, and this is the final solution. So as you can see, there are 2 different parts with 2 different solutions. But which one is the best? Which gives us the best material properties? If you are interested, please don't forget to join us today at 2:30 p.m. We will have the research panel. One of our panelists, Dr. Hamid Kalami, is the person who primarily had worked on this, and he will give us more information about these solutions and the results. Let's move on to our next example, which is one layer multiple materials. This example actually will show us one of the very popular utilities of APlus, which is called AM. Z layer merge. It will merge two different toolpaths by their Z layers. Therefore, the user will have the ability of make one part with different materials or different process parameters. Or if they have like two different parts, but they want to build them on time because it will avoid them having a collision, again, they can use the AMZ layer merge toolpath. Let's have a deeper look on this example. So as you can see the example here, this is all one part. The block, team wall, and the teak wall is all one part. We used AM slice for the team wall, another AM slice toolpath for the teak wall, and then we merged them. We assume that we don't need to build that simple block with DED. So in order to do that, we use containment boundaries for each toolpath. This was the containment boundary for the team wall, and then also Z limits. And this is for the teak wall. We have the containment boundary, and we have the same Z limits, which means we are not making the block, and we are only programming the toolpath in that containment boundary. And then we have our two toolpaths. We will merge them by using AMZ layer merge. I'm going to regenerate our three toolpaths, and then I'm going to show you the backplot. So as you can see on the backplot bar, you can see the blue dark for the team wall, the green for the teak wall, and the toolpath for the Z layer merge. What I would like to mention is our containment boundary and Z limits give us this big ability in order to make one part with different toolpaths. Instead of just splitting it to different parts, we just use the containment boundary. So that's a very good ability. I'm going to show you the final backplot, which is for the merge toolpath. So you can see it's one layer in the middle, two layers for the team wall. This is another functionality of APlus that you can use different layer heights, and it's smart enough to understand that it needs to merge two layers of the team wall with one layer of the teak wall, and it will just build your part from bottom to top. So this gives us the ability to use different materials or different process parameters. Our next example is an aluminum mold with conformal cooling using hybrid wire arc additive manufacturing. Just a quick introduction of this part. So during the COVID-19 pandemic, CAMufacturing joined their COVID-19 engineering research group of University of Windsor in order to help the society. One of the design that the students had was this door handle add-on, which is called J-hook. Because of the shape of it, it will be added and installed on a normal door handle, and then the user wouldn't have to use their fingers in order to open the door, and they can use the door, open the door by using their forearms. So this will reduce the number of times that they touch the surface by their fingers, which means it reduces the number of the possibility of transmitting the wires. But so they designed this. We started to building them using FDM. But what if you want to produce them in? You have a what if you want to have a mass production? What would you do? Because if you're having a mass production, it might not be a good option to use FDM. You might need a mold. Therefore, we did design a mold, and in order to design a mold, we had to design cooling channels as well. So what we designed is a mold block, a cooling channel block, all made by an additive, hybrid manufacturing processes, and it's all one part. But how do we build it? So this is the design of the cooling channel. As you can see, it has been designed on the way that there is no overhang angle if you put it on this surface. So this cooling channel does not have any overhang angle. It can be built from bottom to top. So what we're going to do is to build this from bottom to top, and then we are going to rotate it and use it as a substrate for the mold block, and then build that block on top of this, and then at the very end we are going to machine the mold. So by correct using of APlus and hybrid manufacturing, we built a whole mold and its cooling block using APlus. I would like to mention that on the rest of this presentation, we are going to talk more about the cooling channel because we use one of our newest technology on it, which is called layer merge. So what does layer merge do? Layer merge actually has the ability to merge a bottom to top additive toolpath with the top to bottom machining toolpath. So the result will be one layer deposition, decking, one layer deposition, another decking, one layer deposition, another decking. It means every time that you're depositing a layer, you're depositing it on a smooth surface, so it gives you a better result. So let's have a deeper look on this example. So this is the wire arc toolpath, the additive one. This is the subtractive toolpath, the 2D dynamic contour, and this is the layer merge by APlus. You can choose how many layers you want to merge. I regenerate it, and I'm going to show you the back plot. So we will have the first layer of additive. When it's deposited, we are going to have first layer of machining, second layer of additive, second layer of machining, and then we are going to do the same to the top. You can actually see on the bar how it is shown in the back plot. So this will help many of our clients in the industry with very sensitive parts. And the final result will definitely have a better quality. So let's go to the next and last example of this presentation. Thermal modeling of the DED processes. So we all know how important it is to run thermal studies on directed energy deposition processes. Therefore, we started with this experiment on just a normal block. So if you would like to make deposit material for a normal block, there are different ways. You can have a longitudinal toolpath, you can have a transverse toolpath, or you can have a spiral toolpath, which is basically offsetting the boundaries inward. So you can have all this toolpath, even just for a simple block, but which one has a better result? Doesn't it matter which one we use? Of course it does, and we are going to show it. So this is a temperature versus time graph for all three different toolpaths. You can see on time, that's how it is simulated, the temperature of every element of the block. And what would the result be? So this temperature would affect the stress and strain. So our R&D team members, they calculated the temperature, they simulated the stress and strain on X and Y direction. So the next slide I'm going to show is the X strain of all the three blocks while doing the deposition versus time. So I'm going to show you the final distortion at the end. This is what I was talking about. As you can see, the distortion patterns are completely different. And not also the patterns are different, but also the numbers are different. What does it mean? It means different toolpaths will give you different result. Therefore, this was a simple block. You know, most of our industrial clients, they make very more important and very sensitive parts. So the mechanical properties are important for them. That's why we are working on this again. We are going to add this feature to the APlus to run thermal simulation on your toolpath. Therefore, you can decide which toolpath is better for you, because whatever part you have, APlus would have probably 3, 4, 5 different toolpaths for you, which can make that part. Which one is the best? You will be able to run your simulation and hopefully decide. So this is one of our latest research that is still